In this lesson, we're going to learn another rule for differentiation, the product rule. Now, throughout this lesson, I'm going to teach you how to find the derivative of a product of functions. So the idea is we have some function f and g, and we want to multiply them to make a new function h. Now, to gain deeper insight into this problem, it actually makes sense to draw it as a machine, so I'm going to do that as well. So in this case, we started off with some value x, and then we fed x through f and also through g. Then we took the number we got from both cases and we multiply them to get the value of h. Now, if we want to differentiate h with respect to x, we have to investigate how a small change in the value of x will affect the value that we get out for h. I'd like to do this with an example first, so that you get the basic idea, and then I'll show you how to do it in general as well. So here, I'm going to start with an x value of 2, and then I'm going to try changing x by 5, so we're going to go to 7. I've also chosen h of x so that it's the product of two different functions, root x plus 2 and x minus 1. Now, it's going to help to visualize this with a function machine, so let me go ahead and do that too. So this time I've drawn things a little bit differently, so let me just explain what I've got on the page. The input to this function over here is h. Usually we wouldn't look inside, but I've actually opened up the lid. Now the first thing we do is we take x and we feed it into the square root of x plus 2 to get f of x, which is going to be this first half here. After that we then feed it into x minus 1 to get g of x, which is the second half over here. After we do this, we take the value of f of x and g of x and then we need to multiply them, which I'm going to do in this white square over here. And once we finish multiplying them, we get the value of h of x, which is the final value that we're after. So let me start with our first point, which we said was at x equals 2. Now, if we feed it through this function first, we notice that we're going to get 2 plus 2, which is 4, and then the square root of 4 is just 2. So f of x is also going to equal 2. So now we just feed 2 through g of x, which is x minus 1. Now 2 minus 1 is just 1, so that's what we get over here. And now we'd like to multiply this 2 and this 1 in this white box over here. Now, I'd just like to remind you how we usually multiply two numbers. Let's say I wanted to multiply two numbers, like 3 times 4. The usual way I'd do this is I'd draw a box that's, say, 3 high and 4 wide, and then I'd go ahead and find the area of that box. In a sense, that's the same thing as 3 plus 3 plus 3 plus 3, or 4 plus 4 plus 4. And so, we're going to need to do the exact same things for f of x and g of x over here. So to do this, I'm going to stand f of x straight up, and then g of x can go to the side, like this. And now when we multiply 2 and 1, we're going to get 2, which is just going to be the value of h of x. So now that we know that the value is 2, we also want to see how much h will change when we feed in the next point. Now, if change in x is going to be 5, then the next input point we're going to use is going to be 7. So let me draw that point on too. Now for starters, if we feed 7 into root x plus 2, then 7 plus 2 is 9, and the square root of 9 is just 3, so f of x would just be 3 in this case. And therefore the value of f has just changed from 2 to 3, so change in f is just 1 in this case. We should also copy this to this diagram over here. Now after this, we also want to feed 7 in through the bottom function as well. So since the bottom function is x minus 1, then the bottom value is just 7 minus 1, or 6. Now this time, since we've gone from 1 to 6, we've actually changed g by 5. And again, we should also copy this information to this diagram over here. Now that we know the new values of f and g, we can also use this to draw another rectangle on this diagram. Now since the height is 3 and the width is 6, then multiplying these two just gives you a value of 18. So h of x is 18 for this value. And now it's actually pretty easy to find what change in h is. We just subtract 18 from 2. Now again, we look at this and we say, okay, the value is 16. So what? What's the big deal? But things become a little bit more interesting when you realize that this 16 over here is just the same thing as this area over here. Now this also opens up the possibility to split the area up into these 3 parts that I've drawn here. Let me go ahead and copy on change in f and change in g onto this diagram. And then I'll split this area up into the 3 parts that I talked about. Now let's look at each of these blocks one by one. The first block has a height of 1 and a width of 1, so its area is just equal to 1. Now when we look at this block over here, I want you to notice that its height is 2 and its width is just 5, so its total area is just 10. And then finally we have this box over here, which has a width of 5 and a height of 1, so its total area is just 5. And now, as expected, 1 plus 10 plus 5 is the exact same thing as 16. Now, if we just repeat the exact same steps on the general case, we'll be able to derive a formula to help us differentiate a product like this. Now for starters, this diagram over here doesn't have all the number lines that we had on the last page, so let me start by adding those on first. Okay, so for starters we chose 2 points on the original graph, separated by change in x. After we picked these 2 points, we fed them both through f. And then after this we fed both of the points through g. And now we can call this height over here change in f, and this height over here can be called change in g. Now to find the value of change in h on the output, we're going to need to multiply the values at x and at x plus change in x. And we did that by forming squares from their sides. And then the areas of these two rectangles gave us the values of h of x that we were after. And then finally, the distance between these two output points was the change in h that we were after. Now, as we know, the derivative is just the ratio of change in h on change in x as change in x gets really, really small. Now, usually at this stage, we'd just be stuck. How exactly do we plan to evaluate this thing here? However, an observation that we made earlier is actually going to help us quite a lot here. We said that this change in h over here is exactly equal to the area between these two boxes. And we also said that we could break up this area into 3 other little areas, as I'm going to show you now. Now to actually find this green area, we're going to have to remember what these sides are, so I'll go ahead and mark them from these diagrams over here. Now this first area over here is just going to equal f of x times change in g. And now this area over here is just change in f times g of x. And then we just have to deal with this last area over here, which is just change in f times change in g. Now by looking at this, we immediately notice that change in h is just equal to the sum of these 3 areas over here. So the great thing about this is that we've expressed the change in h, which is a function that we don't know how to differentiate, in terms of only f and g, which are 2 functions that we should know how to differentiate. Now this relationship over here works no matter how large your change in x is. We haven't actually taken any limits yet. However, if we swap this change in h for this value over here, we can actually simplify this derivative into one that we can easily find. Now initially, of course, this looks a lot more complicated, but we can make it a lot simpler just by doing a little bit of algebra on it. As I said in an earlier lesson, a bracket with a limit next to it needs the limit laws for you to work with it. Of course, many courses do prove the limit laws for you, and if you've seen them before, then that's great. But if you haven't proved the limit laws before, it's enough to know that they behave just like normal brackets for simple things like addition and multiplication. Now the first thing to notice is that f of x and g of x don't actually depend on the value of change in x, so that means you can actually pull them out of these brackets. So the first thing we're going to do is we're going to break this fraction up into 3 sums. And now, by using the limit laws, we can distribute this bracket into each of these terms one by one. Now, I've just written this over 3 different lines because I don't have enough space to fit this on one line. Now, the next thing I want you to notice is that this value of f of x and this value of g of x over here don't actually depend on change in x at all. So that means they're constants. And as we know, we can always factor constants out of brackets. So let's go ahead and do that as well. Now, the next thing to say is that this f of x and this g of x here don't actually depend on the value of change in x at all. This means that they're constants, and the limit laws tell us that we can always factor constants out of brackets like this. And now we're ready to actually think about what would happen as we actually took these limits. The first thing to say is that we have this change in f times change in g on change in x. I want you to imagine that change in x is a really tiny number, like 0.0 and then 20 zeros, 1. Well then, change in f and change in g would also be really, really tiny numbers. So let's actually investigate what would happen if we type 2 really tiny numbers into the numerator and 1 really tiny number into the denominator. Now, before I press equals on this number, let's just talk through what these numbers mean. This value, 0.003, represents change in f, and this value over here, which is 0.0001, represents change in g. And this value 0.002 is just the change in x that we use to get the two values on the top. So now if we press equals, we'll notice something interesting. Because all the numbers we put in were very close to 0, and because you're multiplying two very small numbers and then dividing by one small number, the resulting value you get is also really close to 0. So therefore, in the limiting case, we're really imagining change in x to be way smaller than 0.002. And therefore, in the limit, we can comfortably say that this value over here just approaches 0. And now we just have to recognize something to get to our final result. This term over here is just the derivative of g, and this term over here is just the derivative of f. So our final result is given by this. So now we have the final form, but it's a bit more customary to write these terms in the opposite order. And now this formula over here is the product rule. It tells you that if you want to differentiate a function like this, you start by differentiating the first function, leaving the second, then you leave the first and then differentiate the second. Or as I like to remember it, you differentiate them one at a time and then add them. So now I'd actually like to show you how to use this rule. So to do this, let's bring out an example. Now suppose we wanted to differentiate this function over here. First we have to look for subfunctions that we can differentiate. And we can differentiate this x cubed, so it's going to be f. And we can also differentiate x minus 3, so it's going to be g. Now I've copied the function over, so I'm going to go ahead and apply the product rule to it by differentiating each function one at a time. So now that we've actually applied the product rule, it's reasonably easy to differentiate these two functions. This first function differentiates to 3x squared, and this second function over here just differentiates to 1, because it's just a straight line with a gradient of 1. And now, easy as that, we've found the derivative. The derivative of x cubed times x minus 3 is just 3x squared times x minus 3 plus x cubed. Now, if we wanted to, we could expand and simplify this, but I'm not really going to bother with that. I just want to show you how to find the derivatives. Now, just like I did for every other differentiation rule, I also came up with a weird way to write this rule as well. So let me just talk you through this one as well. Each shape represents a different function. And for each function, their corresponding cheeky shape represents their derivative. So this is just saying that if you have a function that's equal to two functions multiplied by each other, then the derivative of the whole function is found by differentiating each one by one and then adding the results. So I'll just go ahead and give you another example to show you how we can use this as well. So I'd always start by actually putting shapes around the functions that I already know how to differentiate. The shape you use doesn't actually matter, as long as you follow the pattern. So therefore, you can differentiate this just by differentiating the first box, and then differentiating the second box and adding the results. And now I'll just go ahead and fill in the derivatives first. And now after this, I'll just copy the original functions into their correct boxes. Just make sure you're careful with brackets whenever you do the product rule, because if you left off these brackets, you'd actually get the wrong answer. Now, if we wanted to, I could expand this and simplify it, but I think what I've got here is enough. I'm sure you could fill in the rest of the steps. Now, of course, if you want to get good at using the product rule, you have to do a lot more examples than the two I've shown here. But these two examples are enough for now. And now I'd just like to summarize this lesson. Throughout this lesson, we tried to differentiate products of functions in the form that we've shown here. To do this, we needed to find a way to write change in h without actually using h at all. We eventually ended up doing this by seeing how change in x propagates through this big machine over here, and seeing that change in h is just given by the sum of these three terms here. After replacing change in h for this, we ended up doing a little bit of algebra and eventually ended up with this final rule, which is the product rule. And finally, you can also write the product rule in this form over here, which just basically tells you that you differentiate each function one by one and then add the results. It turns out that if you had more than two functions, this pattern over here where you differentiate one function at a time and add, keeps continuing. I'm not going to prove this for you myself, but you can easily do it by adding a third function over here and then turning this into a volume rather than an area. And now with this, we've actually completed our discussion on the product rule.